Now, in the last video, we were talking about how we can't use a series of pairwise t-tests to compare the means across more than two groups, because this will lead to an increased rate of a type 1 statistical error, or falsely rejecting the null hypothesis. Instead, we need to use a new approach called an analysis of variance, or an ANOVA, in order to make comparisons across more than two sample means. So an analysis of variance then, or ANOVA, compares the variation among groups to the variation within groups. And what I mean by that is, how different are the sample means relative to the amount of variability that we have within each of those samples. Now, although the name of the statistical test is analysis of variance, we aren't really comparing variances across groups. We are, in fact, comparing means across groups. But an analysis of variance does take all of the variation that exists in the data and sorts out how much of that variation exists among groups and how much of that variation exists within groups. And this is where the name analysis of variance comes from. So in essence, what we're trying to do in an analysis of variance is to assess how much differences there are among groups corresponding to our signal relative to the amount of variation that we have within each group, which reflects our noise. So just like in a two-sample t-test, we're comparing how big the differences are to how much uncertainty we have in our estimates of each of those sample means. And finally, in our ANOVA, what we're testing is a single null hypothesis that all of the true population group means are equal to one another, rather than a whole series of null hypotheses corresponding to each of the possible pairwise comparisons across multiple groups. Now, in this video, we're going to talk about an example where we have three samples that we're trying to compare, but an analysis of variance is appropriate for making comparisons across any number of samples, whether it be 3, 4, 5, 15. The same basic procedures all apply. So in an analysis of variance, then, we're testing the null hypothesis that all of the true population means are equal to one another, and the alternate hypothesis, then, that at least one population mean is different from the others. We don't specify or hypothesize which one, we just test a generic alternate hypothesis that the means are different from one another. So an ANOVA then generalizes our two-sample t-test to more than two groups. If you recall, our test statistic for a two-sample t-test involved a calculation of the difference between the two sample means divided by the standard error of the mean. So in this sense, then, we're estimating the magnitude of differences among means relative to the amount of uncertainty we have in our calculation of each of those means. And so here in graphical sense, then, we're saying how different are these two means from one another in blue, which is our signal in the numerator, versus how much noise do we have within each of the samples, which shows up in our denominator. So in our two-sample t-test, then, we have an estimate for our test statistic that reflects the magnitude of the signal relative to the amount of noise or uncertainty within each of those samples. Now, the same basic principle applies in our analysis of variance. If we took, for example, our numerator and squared it and our denominator and squared it, then we would start to get a ratio of variance components, like the variance between groups relative to the variance within groups. And this is essentially what we're doing when we perform an ANOVA. Now, the key premise of an ANOVA then is that even when the null hypothesis is true and that all of the populations have the same true mean, their estimates are going to differ from one another to some extent just due to sampling error. And so what we're interested in assessing then is whether there's more variation among groups than we would expect to see just due to sampling error alone. So when we perform an ANOVA then, we're asking this basic question: what is the ratio of variation among groups relative to the variation within groups? That is, what is the strength of the signal relative to the amount of noise or uncertainty? Okay, so let's walk through a basic example then of a study that measured the body temperature of round-tailed ground squirrels exposed to cold temperatures, hot temperatures, and warm temperatures. And you can see that each dot in each of these three samples represents a body temperature along the y-axis. And all I've done is to simply jiggle the dots a little bit along the x-axis so that you can see them a little bit better. But the red ones experience cold temperatures, the green ones experienced hot temperatures, and the blue ones experienced warm temperatures. Now, in this experiment, the researchers tested the null hypothesis that mean body temperature is the same for all three groups of squirrels, whereas the alternate hypothesis was that the mean body temperature in the three groups was not the same. Now here is what the data looked like, where each measurement was made on a different squirrel experiencing either cold temperatures, warm temperatures, or hot temperatures, and these are all measured in degrees Celsius. Now we can summarize these observations in each of these three samples using some measurements that you're already familiar with. We can calculate the sample size or the number of observations in each of our three samples. So n referring to the sample size of the ith sample. So our first sample under cold conditions had 20 observations. There were 21 observations under warm conditions and 20 observations under hot conditions. We can similarly calculate the sample mean for each of these three samples, and the sample standard deviation denoted by S sub I, referring to the standard deviation of sample I. So the first sample, the second sample, and the third sample. Now in this example then, we have three samples that we're trying to make comparisons among. And so K in this case is 3, corresponding to our three experimental groups or our three samples. Now, if you recall in our two-sample t-test, we were testing the null hypothesis that these two means were equal to one another and the alternate that those two means were different. And we used a t-test statistic to test this null hypothesis, where our test statistic was calculated as the difference between the two means divided by the standard error of the means. Now, in an ANOVA, we're doing something really quite similar, but in this case, we're calculating what's called an F-test statistic. In this scenario, we're testing the null hypothesis that all three population means are equal to one another, and the alternate hypothesis that the population means are not equal to one another. Now, in this F-test statistic, then, we're simply calculating the differences among our population means relative to the differences within our population means. And here we're calculating these as the mean square between and the mean square within. And the ratio of this signal to noise is calculated as our F test statistic in our ANOVA. And this F test statistic is very analogous to the T test statistic in the scenario where we only have two samples. Now, in the nuts and bolts video, I'll go through the details of how we calculate mean squares in an ANOVA. But for now, we're simply going to refer to this as the differences among our groups relative to the differences within our groups. So in our ANOVA then, we're testing the null hypothesis that all of the population means are equal to one another against the alternate hypothesis that the population means are not equal to one another. We use an F test statistic to do this. which is calculated as the ratio of the mean square between our groups relative to the mean square within our groups. And just like a t-test statistic, we also need to specify what the degrees of freedom are. But in the case of an f-test statistic, we have both a numerator and a denominator degrees of freedom. The numerator degrees of freedom is associated with the number of groups that we have corresponding to the numerator, where we're talking about variation among groups. And this is calculated as the number of groups minus 1, or k minus 1. So in our example with ground squirrels, where we have 3 samples, our numerator degrees of freedom would be equal to 2. But in an f-test statistic, we also have a denominator degrees of freedom, which is associated with the variation within our samples. The denominator degrees of freedom is equal to the total sample size minus the number of groups. So in this particular example then, we had 61 observations across our 3 samples, and we had 3 groups, so our denominator degrees of freedom was 58. Now, if we were to go through and perform the calculations of the mean square between and the mean square within, we could calculate the ratio of these 2 numbers as 1906. So this f-test statistic then is equal to 1906, which tells us how big the differences are among groups relative to the amount of variation that we have within groups. Just like with a t-test statistic, we can compare this calculated f statistic of 1906 against an f distribution with 2 numerator degrees of freedom and 58 denominator degrees of freedom. And we would get a line that looks something like this. And what this blue line represents then is the probability of getting an f-test statistic when we have 2 numerator degrees of freedom, 58 denominator degrees of freedom, and when the null hypothesis is true. So when the null hypothesis is true, most of the time we'll calculate an f value close to 0, and only very rarely will we calculate an f statistic as big as 4 or 5 or maybe even 6. The critical value corresponding to a p-value of 0.05 for an f statistic with 2 numerator degrees of freedom and 58 denominator degrees of freedom is 3.16. So if we calculate an f statistic that's bigger than that, then we would conclude that our p-value was less than 0.05. And so you can see that there's a very small chance of getting an f statistic in the range of 4, 5, 6, or 7 when the null hypothesis is true. Here we calculated an f statistic of 1906, which is huge compared to these expectations when the null hypothesis is true. And so in this case, we would reject the null hypothesis and instead suggest that the more parsimonious explanation is that the alternate hypothesis is true and that there are in fact differences among these population means. Now, instead of performing these calculations by hand, we can perform this analysis using some simple code in R, in particular the AOV command corresponding to analysis of variance, where we specify our continuous response measurement and our categorical predictor measurement corresponding to nominal coding of our 3 treatment groups. Once we've performed this ANOVA, then we just want to summarize the output of this statistical analysis, and the results of this are shown below. Now, it's important to clarify that R gives the results as the effect of the treatment and the remaining unexplained variation, which is referred to as residuals. But what we're talking about in the top row here are the between group effects, and what we're showing in the bottom row here are the within group effects. So you can see, first of all, that the numerator degrees of freedom are here, corresponding to the degrees of freedom among groups. And the denominator degrees of freedom are here, corresponding to the degrees of freedom within groups. So here are our mean squares among groups, and here are our mean squares within groups, and our F statistic, which is simply the ratio of these two. 510.8 divided by 0.3 equals 1906. And the probability of getting an F statistic this big when the null hypothesis is true is actually extremely small. So because p is less than 0.05, we reject the null hypothesis that the population means are all equal to one another, and instead conclude that we have compelling evidence that body temperatures of ground squirrels differ among these three experimental treatments. So we might describe this in a results section by stating that there were significant differences in body temperature among the three ambient temperature treatments, supporting this biological statement with our statistics, reporting our F statistic here as 1906, the corresponding p-value, and not forgetting to specify both the numerator degrees of freedom before the comma and the denominator degrees of freedom after the comma. As an example of this type of analysis from the primary literature, Turco et al. Were interested in studying whether the gill morphology of mangrove rivulus was affected by their exposure to air. Now, rivulus are amphibious fish that can leave the water and survive for quite an extended period of time breathing air. But in order to do this, they have to modify their gills in order to prevent the gills from collapsing and not being able to absorb oxygen anymore. And so they grow these what are called interlamellar cell masses that grow in between the lamellae of the gills to keep them propped open and exchanging oxygen with air now instead of with water. And here's a bar chart with standard errors showing what the mean interlamellar cell mass height was under each of these three samples. Turco et al. Reported that the mean interlamellar cell mass height differed significantly between the three subgroups, and they report the results of their ANOVA with their F test statistic and their p-value. Now, in this case, we have two numerator degrees of freedom corresponding to 3 experimental groups minus 1 and 38 denominator degrees of freedom, which tells me that overall there were 41 fish that were measured because our denominator degrees of freedom is equal to the total sample size minus the number of groups. So 41 total observations minus 3 is equal to 38. Now, just like with any statistical test, an ANOVA has certain assumptions with it. The first assumption is typical of just about all of our statistical tests, and that is that the observations must be independent of one another. Second, the observations within each group must be normally distributed, and that is that the residuals or the deviations between each observation and its group mean must be normally distributed. And without this assumption of normality being met, then we can't reliably use an F distribution to calculate our p-value. And finally, similar to our two-sample t-test, each of the groups in our ANOVA must have equal variances. That is, that the standard deviations within each of the samples must be roughly equal. How equal is equal? Well, as a rule of thumb, if the ratio of the largest to the smallest standard deviation is greater than 2, then we've got a bit of a problem. If the group with the smallest sample size has the largest standard deviation, then we can have some even bigger problems and our p-values can get quite inaccurate. So these are the assumptions then of our ANOVA, and if we want our p-values to be appropriate, we need to make sure that we have met each of these assumptions. So in summary then, An ANOVA is a statistical technique that allows us to make comparisons among more than two sample means. In an ANOVA, the null hypothesis is that all of the group means are equal to one another. An ANOVA functions by separating out how much of the differences among our observations are due to differences among groups as opposed to differences within groups. The test statistic for an ANOVA is the F statistic, which measures the ratio of the among group variance, or how big the differences are among groups, relative to the within group variance, or how much variability we have within each group. We then, like with our other statistical tests, can compare our F statistic to the distribution of F statistics that we would get when the null hypothesis is true, and use that to determine what our p-value is for our statistical test. Now, it's important to remember that an F statistic has both a numerator and a denominator degrees of freedom associated with it. And so when we calculate our p-value then, we're doing that relative to an F statistic that has a certain numerator degrees of freedom and denominator degrees of freedom.